So now we will continue solving questions from chapter 3. So as shown in this figure, a 0.5 kg of ammonia is contained in a piston cylinder assembly, initially at -20 and a quality of 25%. As the ammonia is heated to a final state of temperature 20 and pressure 0.6, its pressure varies linearly with specific volume. There are no significant changes in kinetic and potential. For the ammonia, show the process on a PV diagram. Evaluate work and heat transfer. So, the first thing, we have to show the process on a PV diagram. If we draw a PV diagram, so initial state is at quality of 25%. So it is somewhere here in the mixed vapor region, and it is heated to a final temperature and pressure, and it varies linearly with specific volume. The pressure varies linearly with specific volume. So it is being heated, and it increases linearly. The pressure increases linearly. So it is a straight line. So this straight line can stop in the mixed vapor region, or it may stop in the superheated region. This is not clear from the information. However, we have drawn a straight line. As we will consult the table, we would learn whether it is superheated or whether it is in mixed vapor region. There are no changes in kinetic and potential energy. So evaluate the work and heat transfer. So the work over here is the area underneath the PV diagram. So the work is integral of P dV from V1 to V2. If we take M common from it, it becomes P d V. This V, small v, is specific volume. So this is a trapezium. The area underneath the graph is a trapezium. So the work done for a trapezium is the average of the two parallel sides, taking the average and multiplying it with height. So using this formula, that taking average of two parallel sides, so we know pressure, both the pressures. What we don't know is the specific volume. So for the specific volume, we would have to consult the tables. So V1 would be Vf plus x into Vg minus Vf. We can consult table A13, which is the mixed vapor region table for ammonia. So from there we will find that V1 equals 0.157 meter cube per kg. Now table V2, we need to find V2. We would consult tables and we would find that V2 is in the superheated region. And it comes out to be, if we consult the table, we know both the pressure and the temperature. We would consult table A15, which is the superheated table for ammonia. So we have found V1 and we have found V2. Now we need to find the work done. So we know the formula for the work done. We would input all the values, pressure and volume, and I'm coming back in 5 minutes. Give me some time. So we have found out the work done for the process after finding the specific volumes, and we consulted the tables. Now we need to find the heat transfer. So for the heat transfer for the process, we would write the first law, which is delta U delta KE delta PE Q minus W. From the statements, we know that the change in kinetic and potential energy is negligible. We have found out the work transfer. The delta U is M into change in specific internal energy. So similar to the specific volume, we would consult the tables, and from table A13, which is the mixed vapor table, we would find U1 having quality of 25%, and table A15 we would use to find it is off in the superheated region. So delta U we will find out. So after finding the delta U, we would substitute it in this equation, and we would also substitute W, and the delta U, the Q would come out to be 441 kilojoule. So we have applied the first law, and we needed specific internal energy. So U1, similar to specific volume, can be found out by UF plus X into UG minus UF. Now, next question. So figure shows an insulated copper block that receives at a rate of 100 watt from embedded resistor. I'll be taking questions at the end. So it receives energy at 100 watt. If the block has a volume of 10 raised to power minus 3 meter cube and an initial temperature of 20 degrees Celsius, how long would it take in minutes for the temperature to reach 60 degrees Celsius? Data for copper are provided in table A19. So it's a resistive heater, and it receives energy at the rate of 100 watt. They have given us the volume and the initial temperature. We need to find time in minutes for it to reach 60 degree Celsius. Now, and it's an insulated block. So applying the first law, so delta U delta KE plus delta PE equals Q minus W. So we can assume that there is no change in kinetic energy. This block is not moving. We are not raising the height of this block, so changes of this are negligible. The control volume, the boundary of this block is around the block. So it is insulated. So there is no change in internal energy. There is no change in, there is no heat loss. So there is no heat transfer over here. So we are left behind the delta U and the work done. So in thermodynamics, electricity is work done. So this resistor, we are applying electricity to it. So we are doing work done on the system. And the temperature of it is raising. So the internal energy of this block is being raised. So for solids, delta U is MC T2 minus T1. And the work done that we are doing is minus W dot T. Rate of work done multiply by the time. So we would consult table A19 to find the density of the block. Density is the specific heat. We know the volume, C into T2 minus T1. The rate of work done is minus 100 because we are supplying electricity to the system. So minus 100 into minus is 100. 100 into time. So we will take from table A19, we will take the density and we will take the specific volume. So the only unknown in this equation is time. Time, if we solve right now, it would come out in second. And if we divide that second with 60, we would get minutes. So time would come out to be 22.9 minutes. Next question. So as shown in figure, a fan drawing electricity at a rate of 1.5 kilowatt. So fan is drawing electricity, which is work done, is located within a rigid enclosure measuring, so it's in a room measuring 3 meter by 4 meter by 5. The enclosure is filled with air initially at 27 degrees Celsius and 0.1 megapascal. The fan operates steadily for 30 minutes. Assuming the ideal gas model, determine for the air the mass in kg, the final temperature, the pressure. There is no heat transfer between the enclosure and surroundings, so there is no Q. Ignore the volume occupied by the fan itself and assume there is no overall change in internal energy. So Q is 0, delta U is 0. Sorry, delta U for the fan is 0. Delta U for the fan. But there is change in delta U of the air. So first thing we have to find the mass in kg. So we would apply the PV is equals to mRT. Whenever we apply this formula, so this R is universal gas constant, R bar divided by the molar mass. This universal gas constant is 8314 joules per mole per Kelvin, and this molar mass for air is 28.97. You can remember this molar mass of air, or you can consult table A1, which has molar mass of several gases. So we know the P1 and we know the T1. So P1 and T1 are given, and we also know the volume of the room. So mass of this air inside the room come out to be 69 kg. So now we know the mass. In part B, we have to find the final temperature. So applying the first law, so the room itself is not moving. Our control volume are boundaries around the room. So the room is stationary, it is not being raised, and it is insulated. So we are left behind with this. So now delta U is M specific U2 minus specific U1 minus W dot T. So W dot is, we were given it is 1.5 watt. So that W dot is minus 1.5 because we are doing work done on the system. and U1 we know both the pressure and the temperature, so we can find U1 from table A22. So table A22 is the table of air, and if we know the temperature of the air, we can consult this table and we can find the internal energy. I want you to do it on your own, that you need to look in table A22, look for the T1 temperature and you will find this corresponding uh, internal energy. Now, so the unknown in this equation. So they have also have given us time, for how many uh, time it is heated. It is heated for 30 minutes. So you would convert that minutes into seconds by multiplying it by 60. So the only unknown in this equation is U2. So the U2 would come out to be 257.81 kilojoule per kg. You will consult table A22 again and you will find that corresponding to U2, the temperature would be 354 Kelvin. Now in the last part, they want us to find the pressure at 2. So we would apply the equation of state equation. So we know the temperature, we know that this R is R bar over molar mass. We know part M, we know M for part A, the mass remains same. We know the volume. The only unknown is the pressure. So that would come out to be 0.12 megapascal.
सर के बच्चे ज्वाइन नहीं कर पा रहे.
So the invitation is only for students who are using their Microsoft Teams account. You can send the link. So I've also copy pasted the link in Microsoft Teams. You can copy paste it. You can send it to your other students.
ठीक है सर.
So carrying forward. So as shown in this figure, one side of a rigid insulated container holds 2 meter cube of air at 27 degrees Celsius, 0.3 megapascals. The air is separated by a thin membrane from an evacuated volume of 3 meter cube. So on one side there is air and the other side is evacuated. Owing to the pressure of the air, the membrane stretches and eventually bursts. So now the air takes place in the two volumes. Find the mass of air in kg, the final temperature in kelvins, and the final pressure of air in megapascals. So equation of state, M1 equals P1 V1 over RT1. Similar to last question, comes out to be 6.97 kg. Now our control volume is the entire this surface. So entire boundary. So delta U, delta KE plus delta PE equals Q minus W. So there's no change in kinetic and potential energy because the membrane, the whole body is rigid, it is not moving. It is insulated. So there is no heat transfer. And this boundary that we have drawn, its surface is not moving. The surface area is not moving, so there is no work done. So delta U is 0. So delta U is 0 and delta U is M U2 minus U1 equals 0. So M can't be 0. So M can't be 0. So U2 equals U1. So initial temperature is same as the final temperature. T2 equals T1, which is given to be 300 Kelvin or 27 degree Celsius. Now we have to find the final pressure. So initial pressure for initial state we have this equation, and for final was the top one, initial was P1 V1 is equals to MR T1. If we divide both these equations on top of each other, we would get this. T2 and T1 are same, M and R are same, so we would get this equation. So we know P2 V2. So from there we would get P2 equals 0.1 megapascal. So initially we had a different V1 and after that we would have a different T1. So now one more question. So start reading the statement of this question. So this rigid tank contains 3 kg of carbon dioxide at 500 kilopascal. The tank is initially connected by a valve to a piston cylinder located vertically above, and its volume is given initial volume. Although the valve is closed, a slow leak allows carbon dioxide to flow into the cylinder from the tank until the pressure falls to 200 kilopascal. The weight of the piston and the pressure of the atmosphere maintains a constant pressure of 200 kilopascal in the cylinder. Owing to heat transfer, the temperature of the carbon dioxide throughout the tank and the cylinder stays constant at 290 Kelvin. So, assuming the ideal gas behavior, determine for the carbon dioxide the work and heat transfer. So, we have to find the work and heat transfer. So, the pressure in the tank is 200 kilopascal. So the pressure of the tank is 200 kilopascal. So the pressure remains constant, 200 kilopascal. So for carbon dioxide, the work done for constant pressure is P into delta V. So P is constant, that is 200 kilopascal, and V2 minus V1. The initial volume V1 is of two components due to the cylinder and due to the tank. So V1 is due to cylinder and the tank. The cylinder volume is initially given 0.05 and the tank specific volume, we can apply the equation of state to find the tank specific volume, because we know the initial mass, we know the initial pressure, and we know the initial temperature. So we can find this, all of this. Now the final volume V2. So the final volume